Music has always had a way to connect people regardless of their race, culture, or social standing. Similarly, DNA is a common thread connecting virtually all life on Earth. Any musical piece can be viewed as a sequence of 7 fundamental notes, just like any DNA strand is simply a sequence of 4 fundamental bases. A misplayed musical note can spoil a musical piece. A mutated DNA base can lead to a variety of genetic diseases. But can this music and DNA parallel be developed even further? Miles is a student pianist working on a new composition in music class. He may look friendly, but he's committed a ghastly crime. Little does he know, he's playing the 32nd note wrong. This gentleman is Miles's teacher, and he knows something's off, but he can't quite figure out what sounds wrong with Miles's piece. The teacher has sought help from 3 friends: a renowned older conductor who can only hear the lower register of notes, an established middle-aged conductor who's lost an edge on the higher register notes, and a young up-and-coming conductor who can hear the full range of musical notes.
Stop. It's right there. Time out. Stop. That's not right.
That sounded excellent. Well, Miles, I think based on their responses, the air is a mid-range note. If only there was a method as simple as this to detect a DNA point mutation. This concept inspired us to make a nanobiosensor capable of detecting and identifying a single point mutation in DNA using a binary output method. I'm working on a video here.
So you designed a novel biosensor that gives simple binary results to identify the point mutations?
Precisely. Using a technique known as dip pen nanolithography, we are able to immobilize DNA bait strands on a glass substrate. By printing these bait strands, we are able to concentrate them into a sub-micron sized dot. When incubating with the target sequence, these concentrated dots are able to hybridize with the target strands from a very diluted solution. This allows us to pull target strands out of solution and into a much smaller volume, which effectively concentrates the target DNA to detectable levels.
But how do you quantify the signal?
We use bait strands modified with a fluorophore to test for a point mutation at a specific site. If the complementary strand indeed has a point mutation, the bait-target hybrid will form a bulge at the point of the mutation. We then perform 3 different tests utilizing chemical compounds that specifically react with only certain types of mismatches. These chemicals cut the bait strand at the bulge, giving us shorter sequences of DNA. Hybridized strands that undergo cleavage will lose a segment of the bait strand above the site of mutation. Since this segment of the bait strand possessed the fluorophore reporter, the result will be a loss of fluorescence. Therefore, presence or absence of the fluorescence signal is a direct indicator of whether cleavage occurred or not. Depending on which of our chemical tests produce a positive result and which ones produce a negative result, we can tell precisely the identity of the point mutation.
Sounds like this technology has a lot of potential in diagnosing genetic diseases or predisposition to various cancers.
That's right. Now let's get going. We're going to be late for that concert.